Latitude Media, covering the new frontiers of the energy transition.
I'm Shayle Kann, and this is Catalyst.
Waste heat is a waste of time because people are chasing after a small increase in COP to justify and minimize OpEx, but what they've inadvertently done is essentially driven a massive increase in CapEx by trying to capture waste heat.
Coming up, the story of steam.
Do you want instant access to energy storage supplier pricing that's project-specific? Or the ability to compare domestically made battery and PCS options across the market? ANSA now offers the industry's first battery energy storage data and analytics platform to make better development and procurement decisions. ANSA provides in-depth commercial, technical, and risk data and analytics to help developers choose the best equipment for any project. Improve your returns and save months of evaluation time with ANSA. Learn more about ANSA's energy storage subscriptions at go.ansarenewables.com/latitude or click the link in the show notes.
Imagine a world where connected devices like EVs, home batteries, and smart thermostats work together to support a more efficient and reliable power grid. Well, you don't have to imagine it anymore. This vision is a reality today thanks to EnergyHub. With EnergyHub's Edge DERMS platform, utilities can create virtual power plants through customer-centric flexibility programs, making it easy to manage distributed energy resources and balance the grid. Unlock grid flexibility and reliability through cross-DER management with EnergyHub, the trusted Edge DERMS leader. Visit energyhub.com to learn more.
I'm Shayle Kann. I invest in early-stage technologies at Energy Impact Partners. Welcome. Let's start with a number, 50%. That's roughly how much of all industrial energy use globally goes to generating steam. How do we make steam today? Well, we boil water. It's basically that simple. It's what drives paper mills, food processing, chemical production, textile manufacturing, you name it. Steam is the silent workhorse of industry. And right now it's mostly powered by hydrocarbons. Depending on where we're talking about, it's natural gas or maybe even coal, could be oil in some places. We heat water into steam, and that keeps our industrial processes humming, which makes decarbonizing steam not just a niche technical challenge, but a big emissions opportunity basically hiding in plain sight. So what are the options? And also, what about all that waste heat that often tantalizes entrepreneurs looking to turn waste into value? Well, let's explore. To dig into that, I brought on someone who basically spends all day thinking about this. Addison Stark is the co-founder and chief boilermaker, his term, of AtmosZero, which is an EIP portfolio company, I should note. They're developing what they call Boiler 2.0, which is a heat pump-driven electrification solution for industrial steam. Here's Addison. Addison, welcome.
Shayle, longtime listener, first-time caller, I suppose.
Excited to have you school me publicly, which you've done privately many times, about industrial steam. Talk to me about the market for industrial steam. What is it? Where do we use it? How big is it?
You know, as the true thermodynamicist, mechanical engineer that I am, I actually want to take a step back first and say, well, what is steam, right? I mean, and why do we care about steam, and why am I excited to tell you and talk about it today? Steam is gaseous water, but it's been the most important working fluid that we've had in industry and the built environment since 1867, when Babcock and Wilcox patented the combustion boiler. They moved from a brick-by-brick built combustion systems on site to a factory-built boiler that really was the lubricant to, or the catalyst to drive the Industrial Revolution. It's really meant that all of industry has been built around this super valuable working fluid. The amount of heat that can be delivered through the phase change of water, the latent heat of vaporization or condensation, is tremendous. It allows us to actually have very compact chemical processes, phase change separation being used in chemical facilities, but also it is what has driven heating in the built environment for just as long. Some of the oldest boilers that I've seen are generally things that have been delivering both heat to industry in London, but also to buildings to keep them warm. And we use the same form factor today. Today steam accounts for about half of all industrial heat that's being delivered. It's the most important working fluid in industry, and it is an outsized impact in the food and beverage industry, the chemicals industry, pulp and paper, pharma, personal care products, cosmetics. Wherever you think of a biological process or cooking, steam is being used.
And how much is steam? I guess what I mean to ask is I know that one way to divide up the market for industrial steam is by temperature requirement. So obviously there are different temperature gradients of steam that are required. But beyond that, are there any other ways that you distinguish between different types of steam that are required for different applications?
Well, that's a great distinction, right? When I first got into industrial heat, it was back during COVID. I was doing two things. I was, baking sourdough and then grinding my axe against this idea that industry was hard to decarbonize. And I really got into this question of what's most important. And you start to look at industrial heat, and as exactly as you put it, people look at temperature ranges, but then working fluids. And then each working fluid, like steam in particular, can be subdivided. There's kind of two different ways we think about steam. In the chemicals processing where steam is used as a reactant, it's known as what we call superheated steam. It's essentially purely gaseous. It's not dissimilar to nitrogen or oxygen or any sort of a pure ideal gas. However, what is used most commonly to deliver heat is known as saturated steam. Essentially, steam sitting right in equilibrium with liquid. It's going back and forth between the phases of liquid and gaseous, but that's where all of that potent thermal transfer is, where you can really get a ton of heat transfer. So, the majority of heat delivery that's done by steam is all through saturated, and that's what boilers deliver today. Generally, all of this is, almost all heat delivery through steam is done around 225 Celsius and below. Generally, that above there, you run into some heat applications, but a lot of reaction applications as well.
Okay, and so mostly what we're doing in terms of heat applications, you said 225 C and below, and that's where we're using boilers, right? What has changed? You mentioned the original Babcock and Wilcox patent in the 1800s. How similar or different is today's industrial boiler versus what came in the 1800s?
From a first pass, an engineer who worked at Babcock and Wilcox in the 1867, as part of that, would recognize what we use today. The same form factor, we're essentially burning fossil fuels to boil water to be able to deliver saturated or supersaturated or superheated steam to processes. But there have been improvements on the fire side, ways to continue to improve the efficiency of how much of the chemical energy we're able to convert to steam heat has continued to improve. Also focuses on minimizing not just CO2 emissions, so that comes from efficiency, but then also on SOx, NOx, particulates, other sort of criteria pollutants. There's been continued improvement on that, mostly driven through regulation, but it's the same product, and that's the reality, and the whole market for boilers has largely built around that fact, which is a factory-built combustion device that's able to deliver steam in a very highly efficient way and integrated in a very smooth way.
Let's talk a little bit about the economics of steam delivery. You mentioned that what we're doing is burning fossil fuels. The first question is, which fossil fuels are we burning where for industrial steam?
Yeah, steam, that was a bit of an oversimplification on my part. Steam is generated not just with fossil fuels, but some places you're using electricity, some places you're using biofuels. But yeah, today in North America, predominantly we're burning natural gas. In Europe, that's driven by LNG, but in China, in other developing markets, you still see utilization of coal, and even some places where you don't have access to import of natural gas, you're often using even oil or bunker fuel. Some places where you see some effort towards decarbonization has been done, people will be using biomass boilers, or if you just have enough forestry resources, this is very common in pulp and paper, just to use that directly. Or you see the utilization of RNG in Eastern Europe, in North America, where that kind of a market has been matured.
Okay, so talking about the economics then, to a first order, is the cost of industrial steam basically a function of the cost of that underlying fossil fuel commodity? Like, does the cost of industrial steam in North America vary directly with the cost of natural gas, essentially?
Yeah, so the cost of steam is really dominated by the fuel cost. Like any sort of a energy conversion process, the capital is important as an upfront cost, but once you look at the 20-year life cycle of a boiler, or sometimes we're out in the field and we see 30, 40, 50-year-old boilers, it's really about the OpEx, the fuel, and the maintenance, but fuel itself can be 70 to 90% of that OpEx itself. So it's the dominant factor in the cost of steam delivery. In North America, natural gas is cheap, and it really is the dominant fuel in steam generation for industrial facilities.
And what kind of costs are we talking about? And like, I guess the other question is, and this will vary by application, but how important is the cost of that steam to the ultimate cost of whatever product is being produced? Is it a major cost driver for the end product, or is it pretty de minimis? Like, do they care? How much do they care?
So different industries have different exposure to the cost of steam in the ultimate delivered product, right? If you look at food and beverage industry, generally the cost of steam is a small fraction of the delivered product, because at the end of the day, let's say you're brewing beer. You're dominated by the cost of hops and barley and other sorts of ingredients. And while your most important Scope 1 emissions are from the boiler on site, it's a rather small impact on the embedded cost. So there is room for innovation there. But if you look at the cost of steam today in facilities, it's really a function of what are you getting your natural gas at the facility cost itself, and that varies widely. So it's really, you look at the natural gas cost that you're paying, add on a small, like we were estimating before, 10% from the capital, and that really becomes kind of your levelized cost of steam that you're utilizing in the facility.
Catalyst is brought to you by ANSA. ANSA offers a one-of-a-kind data and analytics platform and advisory services to support better project development and procurement decisions. For energy storage developers, ANSA's platform provides crucial information that you never had easy access to before. Now at your fingertips is real-time pricing for a long list of system configurations to suit any project. ANSA provides a 360-degree view of the market with lifecycle cost analytics and commercial, technical, and risk data. With ANSA, developers can easily determine which products to use in their designs, finance models, and RFPs. Learn more about how ANSA helps save time and maximize profit at go.ansarenewables.com/latitude.
Catalyst is brought to you by EnergyHub. EnergyHub helps utilities build next-generation virtual power plants that unlock reliable flexibility at every level of the grid. The EnergyHub platform takes the guesswork out of balancing energy supply and demand. It uses machine learning to control customer-owned distributed energy resources, like EVs, home batteries, and smart thermostats, to precisely shape load profiles for grid flexibility and reliability. As the industry leader, EnergyHub helps more than 80 utilities manage 1.6 million devices. That's more than any other Edge DERMS on the market. Click the link in the show notes to learn more, or go to energyhub.com.
Okay, so let's assume one cares about decarbonization and one comes to the realization that half of the industrial energy in the world is delivered as steam, and that we want to do something about the emissions associated with that, which is a huge bucket of emissions. Let's talk about the different pathways for decarbonization. The first one, I think that maybe is, you tell me if you feel differently, but maybe is, I guess, the most mature, or at least most widely adopted today, is just like electrify the boiler, make a resistance boiler, right? And instead of burning a fossil fuel, you use electricity to heat the water. How much of that is out there today, and like what are the limitations of it?
You're right that probably the most off-the-shelf solution for electrification of the boiler room is resistive or electrode boilers. Sometimes they're known as a trade. It really depends on how high a voltage and how high of a throughput you're putting through. And while the total penetration in the market is relatively small, maybe about 1% to 2% of the boiler market today, it's the fastest growing subsector in the boiler market. So if you look at the growth of the boiler market, it's about a $17 billion a year market with 6% growth per year. But electric resistive boilers are growing at about 26% per year. When people are looking to electrify, when people are looking to move away from combustion, what's available off the shelf today is a resistive electric boiler. Of course, you're signing up for higher cost, right? We were just talking about how expensive natural gas is. Generally, if you're moving from a natural gas steam to electric steam, you're looking to a 2 to 3x increase. Really, you're just increasing relative to what your facility's spark spread is. Now, the other off-the-shelf solution that manufacturers have is really geographically dependent. Do you have access to either biomass or RNG? These are similarly large increases in OpEx as well, just because the fuel cost is much more expensive than natural gas here in the US, where natural gas is so cheap.
Okay, so then the alternative, if you want to electrify, is what you guys are focused on at Atmos, which is using heat pumps. We've talked a bunch about heat pumps on this podcast before in the context of residential for the most part. I think people appreciate Andy Lubershane, who I know you know well, and our listeners have heard many times, talks about the magic of heat pumps, the concept of basically getting more energy out than you put into it. In some ways, heat pumps seem like sort of an obvious solution here if you could make them big enough and powerful enough. Why, in your mind, have heat pumps not taken off more? Why is it that the most mature thing is the resistive boiler and not the heat pump today?
Well, as the thermodynamicist at heart, I need to take issue with the magic statement. Obviously, it's only magic insofar as it still satisfies the first and second law of thermodynamics. And we are, of course, getting more, let's call it usable energy out. We're getting, in a heat pump, you can get anywhere from 2 to 3x of the heat out of the electricity put in, but where is that heat coming from? We're sourcing it from somewhere, right? Industrial heat pumps have been, let's call it a nascent market for 30 years. Essentially heat pumps that go much higher in temperature than residential heat pumps, because ultimately you got to get up to above 100 Celsius to be able to deliver steam. So how people have traditionally tried to do that is they've captured waste heat in the facility. They'll go after and find some sort of a source from a unit operation on the manufacturing floor, capture that, and then upgrade it. Now, that has kept it to the point where essentially every facility has been bespoke. So waste heat is often mismatched in time, temperature, or location relative to steam demand. And it's led to bespoke, expensive, and slow to deploy projects. The tangent or the little pithy thing that I like to say is waste heat is a waste of time. It's actually limited this industry for some time because people are chasing after a small increase in COP to be able to justify and minimize OpEx. But what they've inadvertently done is essentially driven a massive increase in CapEx by trying to capture waste heat. At Atmos, what I thought about and really what led to why I really got interested in can we do heat pumps better is how do we standardize them, productize them, and what we saw was an opportunity to go air source to avoid waste heat. So, that's one view that I have of a drop-in mass manufactured approach. There are a couple other ones as well, but I think that this is a scalable way to go after it.
Let's stay on that tangent for a minute, because I do think it's an interesting one. I like your phrasing, waste heat is a waste of time. So waste heat is this like tantalizing mirage that I feel like I see entrepreneurs and academics and all sorts of people going after with a regular cadence, because, and not just for the purpose of running a heat pump, but in general, there is so much industrial waste heat, right? And so you look at those numbers, or you look at one of the Sankey diagrams, and you see how much energy we waste from industrial processes. And you think, gee, it sure would be nice if we could use that waste heat. And oftentimes the waste heat is, sometimes it is used in some processes. But when it's not, it's often because it's too low temperature to actually do anything with useful on the site. So then you think, okay, great. Well, I've got this waste heat that is hotter than ambient. And so it should be cheaper for me to upgrade it to whatever temperature I need. And if only I could do that, like this is just an opportunity hidden in plain sight. And so I see it very commonly that people, whether it's running a heat pump or something else, want to do something with waste heat. And you, along with Greg Teal on our team, have been on I think a long-term tirade to say it is a mirage, basically. It's not that it doesn't exist. It's that accessing and utilizing waste heat industrial facilities is way harder than you think it's going to be. So can you describe in a little bit more detail why that's your view?
It's in the words, right? I mean, waste heat is waste. And at the end of the day, we've got to get it out of the facility. And that's just obeying the second law of thermodynamics. Now, I'm not going to go down a deep thermodynamic tangent here, but there are a couple of scaling things to think about. So there's two things that people try to do often. Well, three things probably with waste heat. Number one, capture it and upgrade it in a heat pump to be able to deliver heat. Number two is capture it and try and convert it into electricity. Or number three, capture it and utilize it to drive processes for chemical processes or separations or something else. For all of those things, you essentially need to find a way to capture that waste heat. And that's where the first most expensive step comes in. The lower the temperature it is, you need to have larger heat exchangers to be able to capture that and put it into the other working fluid. That increases CapEx. The other thing is this waste heat is not always located in the exact same place at the exact same temperature in every given facility. So you're building bespoke one-off heat exchangers with very expensive engineering hours to go and build and capture that in that facility. And so if you're a manufacturer, say you're a global cosmetics manufacturer and you have 20 manufacturing facilities around the world, your facility in Europe might not look like the one in South America, actually has slightly different temperatures of waste heat, different locations. You cannot take what you did to capture that waste heat in one facility and apply it in the other. So there's no real scales of mass manufacturing or volume to be able to gain there. It's all about, are you going to be able to get the economic value of that waste heat on a project by project basis? So there's two challenges that I see. Number one is waste heat destroys repeatability of any given solution, no matter what you're trying to do. And of course, right there is what you see is when we look at what has successfully scaled in climate and energy technology is things that are manufacturable, modular, repeatable. That's why the boiler was successful, right? There was nothing, it was the transition from bespoke boilers to mass manufactured boilers that allowed the Industrial Revolution to go. We shouldn't assume that we can continue to do bespoke approaches. The second challenge with waste heat is this fact that it is waste, it is low value. Heat carries this other thing. It's not just the energy, but it's also the entropy associated with that heat. At the lower the temperature, the relative fraction of energy to entropy is decreasing. Essentially, the total usable energy in there is much lower. So you have to do more work just to actually get something out of it, and there's less to get out of it. So it has been tantalizing. For 30 years, it's kept industrial heat pumps to be a very limited and one-off bespoke industry, and no one has really been able to scale. And that's what that nut is that we're trying to crack, both at Atmos Zero and I hope through Greg's input that you guys are continuing to fight the good fight with us.
So obviously the challenge with doing what you're doing, though, I mean, the reason that waste heat seems nice in the context of delivering industrial heat with a heat pump is that you're starting at a higher temperature than ambient. So if what you're doing is air sourced, which you are, then the challenge is you need a big temperature lift, at least relatively speaking. You need to get from ambient up to 100 degrees C or more. Talk to me about what that actual technical challenge is. Like, what are the mechanics of a heat pump that make the higher the temperature lift, the harder it is to do?
Well, first off, there is a little bit of a trade-off an economic trade-off that you hit immediately. theoretically, the higher the lift that you're trying to go in a heat pump, the lower your overall COP, coefficient of performance, the overall efficiency you can achieve. So by ignoring waste heat, you're actually decreasing the total efficiency you can achieve, which is a trade-off, right? We're essentially looking at decreasing our overall efficiency, but ideally to be able to massively decrease CapEx. Now, the challenge there is, well, we have more CapEx in this kind of a solution because you need to have a higher lift heat pump. So in order to overcome that, you really just need to focus on having a multi-stage approach. Essentially think about taking two heat pumps and stacking them on each other to be able to get up to the temperatures you need to do. Now it's managing complexity at that point. But ultimately, when you think about building heat pumps to be able to deliver steam, you want to focus on having something that is highly efficient but repeatable, just like the boiler, and that's what we focused on.
I guess let's talk finally about the economics again. Rounding back to that, you mentioned this before, but this is true of all electrification things. You have this challenge of the spark spread, which is the difference between the price of electricity and the price of natural gas, basically. And when you're electrifying, electricity is in North America. Let's talk geographically too. North America, electricity is way more expensive than natural gas, basically. And so, therein lies your unit economics challenge if you want to decarbonize or if you want to electrify. Of course, with heat pumps, you make some of that up with your COP. So the fact that you have this efficiency can help a little bit. What do you think it takes to get truly economic industrial heat pumps in North America versus in Europe, where I know the equation is very different?
You're getting to a very important point in, let's call it industrial heat decarbonization, no matter what working fluid. The challenge, and particularly it's the US, not just all of North America, but in the US, is the fact that we have natural gas resources that are incredibly plentiful and incredibly cheap and well integrated in infrastructure. We have massive natural gas pipelines that go to every industrial facility, and we have therefore very low cost access to steam, process heat, anywhere. That is a challenge for any sort of an approach here. We know that it has limited the deployment of resistive boilers here because you're just signing up for a direct one-to-one switch to electricity prices instead of gas prices. But then the two approaches that allow cost-effective ways is, as we've been talking about, and what we do is heat pumps. Through increasing the efficiency through a high enough COP, you can bridge that spark spread gap. And the other approach is thermal storage, right? And so I know, and we're excited about thermal storage as kind of that complementary approach where when you have access to time-of-day pricing with renewables, you can hopefully drive down that cost low enough through charging those and deploying those. That's the two approaches. Now, it's different suited for the different kinds of facilities that use steam. Very large facilities with access to time-of-day PPAs or behind-the-meter renewables is a really great place for thermal storage. We see that as an excellent opportunity and also for higher temperatures. However, for lower temperature steam, think below 200 Celsius, where you might be an end-of-the-wire price taker for electricity, you need to have a high enough COP to be able to bridge that spark spread. That's where heat pumps can win, because not only are heat pumps an ideal solution there because of the low temperature, but you can get a high enough COP to actually use just direct industrial tariff electricity off of the grid and not worry so much about having to also engage in the electricity market as an end user. The reality is, when you look at manufacturing in the US, 65% of manufacturing facilities have a thermal load below 10 megawatts. So really you need small enough scalable solutions that look like boilers to be able to be a solution for call it the light duty manufacturer.
Okay, so that's the US with our plentiful, cheap, beautiful natural gas. What about Europe?
Everything changed in Europe after the invasion of Ukraine, the sabotage of Nord Stream. No longer do you have a ready and plentiful access to pipeline gas coming in from Russia. So now in Europe, natural gas prices are much more closely pegged to global LNG imports into Europe, and that has changed the spark spread there and the equation there. But it's not just about raw economics from a spark spread standpoint. The other economic impact in Europe is access to steam to keep manufacturing up and running is a critical utility in manufacturing. So thinking about supply chain and energy security is just as an important impetus to transitioning to an electrified solution for Europe beyond just the raw spark spread.
Addison, this was fun as always. Thank you so much for joining.
Shayle, this was great. As we like to say around here, full steam ahead.
Addison Stark is the co-founder and chief boilermaker of Atmos Zero. This show is a production of Latitude Media. You can head over to latitudemedia.com for links to today's topics. Latitude is supported by Prelude Ventures. Prelude backs visionaries accelerating climate innovation that will reshape the global economy for the betterment of people and planet. Learn more at preludeventures.com. This episode was produced by Daniel Woldorff. Mixing and theme song by Sean Marquand. Stephen Lacey is our executive editor. I'm Shayle Kann, and this is Catalyst.